Commander, let's light the sky. Training sharper drone pilots, learning how to fly. Mission ready mindset, safety leading every plan. Skills that build confidence from takeoff through the scan. Tune in at Sky Commander, come join the crew today. Learning smart, fly with purpose, level up your way. We see more, no sooner, that's the edge we're here to spread. See above, go beyond, get ahead.
Okay, let's get started.
So picture this. It's 2024, and this major civil engineering firm just poured, 10,000 tons of concrete for a new commercial subdivision. This is for their primary drainage system.
Oh, wow. 10,000 tons. That's a massive pour.
Right, a massive pour. And then a week later, the traditional surveyors come out to do the final as-builts, and the project manager's stomach just completely drops.
Let me guess. The grade was off.
The entire grade was off. The water was literally going to flow backward, straight into the foundation of the anchor retail building.
Oh, man, that is a total nightmare scenario.
Yeah, and the crazy part is the culprit wasn't the concrete crew. It wasn't the guys running the heavy equipment. The entire disaster, it all traced back to this microscopic laser measurement taken by a drone like 3 months earlier.
Right, because they trusted the raw digital twin.
Exactly. The data looked incredibly beautiful on the screen. It was this perfect 3D digital twin of the site. It looked like pure reality just captured in a bottle.
Yeah.
But it was dead wrong.
Yeah, and that distinction right there, the distinction between a pretty 3D model and a raw field of evidence, that's the dividing line between an amateur who just bought a shiny new payload and a professional data provider.
Oh, absolutely.
Because it is incredibly seductive. You look at this high density point cloud on a 4K monitor and you just feel like you possess the absolute truth about that physical space. The human brain just naturally wants to connect those dots.
It looks so real, you just assume it's right.
Exactly. But a professional operator looks at that exact same point cloud and they immediately question the workflow that generated it. Like, what exact wavelength did the sensor use?
Right.
How tightly coupled was the GNSS and the inertial measurement unit? How aggressive was the noise filtering algorithm? Because if you don't understand the physics of the actual capture, you're essentially gambling with your client's liability.
Okay, let's unpack this. Because going from that perceived magic of a flying laser to the granular mathematical truth of remote sensing is just a brutal learning curve.
It really is. It's a huge paradigm shift.
And our mission on this deep dive is to deconstruct how these 3D worlds are really built. From the physics of a single photon all the way up to the complete regulatory nightmare of heavy lift drone operations.
Which is a lot to cover.
It is. And we're looking at a pretty extensive stack of source material today. We're pulling from advanced photogrammetry journals, surveying standards, aviation regs, the works. Mm-hmm. And we are assuming that you, the listener, already know your way around a drone and a basic mapping mission.
Right. We aren't here to explain what a z-axis is.
Exactly. We are here to talk about why your z-axis is, drifting 15 centimeters into the dirt the second you fly over a metal roof.
Yeah. And to understand those macro level failures, like that drainage disaster you mentioned, we have to start at the absolute micro level.
Down to the single point.
Down to the single point, the foundational building block of this entire industry. When we talk about point clouds, we have to really conceptualize what one single point actually represents. And the source material uses this great visualization, the paint sprayer analogy.
Oh, yeah, I love this one.
Right. So imagine dragging a high-pressure sprayer full of completely invisible microscopic paint across a landscape. Millions of these tiny droplets stick to the canopy, the power lines, the terrain.
Just coating everything.
Coating everything. But what's crucial is that those droplets are not just spatial markers. They are dense data packets. Every single point contains an X, Y, and Z coordinate derived from the trajectory, but also, an intensity value, a discrete return number, a scan angle, and a GPS timestamp that is accurate to the microsecond.
But the thing is, one point is entirely useless on its own.
Completely useless.
Like, one point isn't a tree branch, it isn't the edge of a curb, it is simply circumstantial evidence that a pulse of light left the scanner, traveled through the atmosphere, hit some surface with enough reflectivity to bounce back, and then reach the receiver before the timing gate closed.
That is all it is.
Just circumstantial evidence. We are stringing millions of these little circumstantial events together to try and infer a structure. And I think one of the most misunderstood pieces of evidence in that packet is the intensity value.
Oh, without a doubt.
It's basically the amplitude of the return signal, right? The literal acoustic loudness of the light bouncing back.
What's fascinating here is how operators just completely misuse intensity. They try to treat it as if it's a monochromatic photograph.
Like a black and white picture.
Exactly. And it isn't. Intensity is a super complex measurement of surface reflectance, and it's dictated by the material properties at a very specific laser wavelength, usually either 905 nanometers or 1550 nanometers.
Right.
But it is incredibly valuable for identifying material transitions that are geometrically identical. So say you are mapping a highway. The physical elevation of the asphalt and the painted lane stripe next to it are practically identical.
Geometrically, they're the same flat surface.
Right. But the titanium dioxide in that white paint reflects the 905 nanometer laser wildly differently than the surrounding black betamin.
But wait, looking at the field guides on this, the environmental variables make intensity a complete wildcard if you aren't controlling for them. Like, I go back to the flashlight analogy.
Yeah.
If you shine a flashlight at a mirror versus black cloth, you get a different bounce.
Sure.
But what if it's wet out? If the asphalt is wet from just a morning dew, the water absorbs that near-infrared energy, and your intensity values just plummet into the abyss.
Oh, they tank. Absolutely.
Or if your drone banks into a turn, changing the angle of incidence, the beam scatters away from the receiver instead of reflecting straight back, which completely alters the intensity of the exact same patch of dirt.
Right.
So if it's so volatile, why do we even use it to classify materials?
Well, because you don't use it in a vacuum. A professional understands the moisture conditions at the time of the flight. If the entire road surface shows a degraded intensity, but the relative difference between the asphalt and the gravel shoulder remains proportional.
Oh, I see. So the ratio is what matters.
Exactly. You can still automate the extraction of the road edge. You just have to calibrate your extraction algorithm to the localized environmental conditions of that specific flight line. You are reading material response, not true color.
That makes total sense.
But, the data packet that truly drives the financial value of LiDAR, the metric that engineers actually base their concrete pours on, is the elevation.
And this is where the physics of the capture just get terrifying. Like, the ladder analogy from the sources breaks this down perfectly for clients who don't understand why a drone LiDAR rig costs $100,000.
Right. It's not just a fancy camera.
Not at all. If you are standing in a room and you want to measure the exact elevation of the ceiling, you could stand on a ladder and use a laser tape measure. But the distance from the ladder to the ceiling is just a raw range.
It doesn't give you the room's actual elevation.
Right. To know the actual elevation of the ceiling relative to the building's datum, you have to factor in the height of the ladder, the exact XY position of the ladder on the floor, the tilt of the ladder if the floor is uneven, and the precise angle you are holding the tape measure.
And that's just standing still. Now, I want you to imagine strapping that ladder to an airframe moving at 15 meters per second.
Just flying through the sky.
Right. The drone is vibrating violently from the propulsion system. It is pitching, rolling, and yawing through all these invisible micro-turbulences in the air column. And the laser scanner beneath it is firing hundreds of thousands of times a second, just sweeping back and forth.
And every single one of those pulses is a tape measure reading.
Every single one. To turn that raw range into a usable elevation coordinate, the system must instantaneously solve the position of the drone in 3D space, the exact attitude of the airframe, and the dynamic angle of the scanning mirror, all synchronized to a microsecond accurate GPS clock.
It's honestly a miracle it works at all.
It really is pure math and physics.
So we have this violently moving platform firing lasers, and then those lasers hit something incredibly complex and porous, like a dense pine forest. And this leads straight into what is probably my biggest pet peeve, and it's the biggest marketing lie in the remote sensing industry.
Ah, I know exactly what you're going to say.
The idea that LiDAR sees through trees.
Yeah, the X-ray vision myth.
Yes. People talk about it like it's a medical X-ray penetrating solid matter. It drives me crazy. Solid wood is opaque to near-infrared light. A 905 nanometer laser does not phase through an oak leaf.
No, of course not. It hits the leaf, and that specific photon bundle is stopped, absorbed, or reflected. The reason we get ground data under a canopy isn't penetration, it's beam divergence and gap probability.
Let's break that down, because I think people picture a laser as a tiny, infinitely small dot.
Right, like a laser pointer. But a laser beam is not an infinitely small point of light. As it travels from the drone to the ground, the beam actually spreads out. At 100 meters above ground level, the footprint of that single laser pulse might be 10 to 15 centimeters wide, depending on the sensor's optics.
Exactly. So when that 15-centimeter beam hits the top of the canopy, maybe 30% of the light hits a cluster of pine needles. That energy reflects back to the sensor. The sensor records the time of flight and registers it as return number 1.
But the beam isn't done.
Right. The other 70% of the light within that exact same beam footprint continues traveling downward through the microscopic gaps between the needles.
And that is the canopy elevator effect. The remaining energy just continues riding down the elevator. So maybe another 40% hits a lower branch a split second later. That reflects back. Return number 2. The final 30% manages to thread the needle all the way down to the forest floor, bounces off the dirt, and returns to the sensor. Return number 3, or what we call the last return. The system just recorded 3 distinct vertical elevations from one single pulse of light because the beam footprint fragmented across a porous target.
Okay, but there is a massive trap here.
Right.
Because people blindly trust the phrase last return. I've seen workflows where the operator just applies a global filter like isolate last returns equals ground.
Oh yeah, the automated ground button.
Right. They just run the macro and export a digital elevation model to the client. But what if the understory is impenetrable? What if it's a dense thicket of blackberry bushes and that 15-centimeter beam footprint is completely exhausted by the time it hits the top of the brush, like 3 feet off the ground?
The pulse dies right there.
Exactly. The sensor records the top of the brush as the last return. So if you export that as your ground model, you have literally engineered a fake floating terrain that sits 3 feet higher than reality.
Which brings us right back to your opening example with the drainage ditch. If the surveyor assumes the last return is the ground, the software builds a terrain model over the tops of those blackberry bushes. The civil engineer designs the pipe inverts based on that false terrain. The concrete is poured, and boom, the water flows the wrong way.
Because they trusted the elevator, but the elevator got stuck on floor 3.
Exactly. This is why you cannot automate professional judgment out of the workflow. The operator has to actually look at the point density. They have to analyze the cross-sections. If you only have 2 points per square meter making it to what you think is the ground under a dense canopy, you do not have a reliable bare earth model.
You just have a statistically weak inference.
Perfectly said.
And this really highlights the critical difference between the icing and the plate. Like photogrammetry matching pixels from overlapping photos, that only gives you the icing on the cake. It models the outer visible envelope of the forest canopy.
Because it can only map what it can see.
Right. LiDAR gives you the potential to capture the icing, the internal cake layers of the branches, and the plate underneath. But you only get the plate if the physics of the environment actually allow the light to reach it.
And once you've collected all those returns, you still don't have a map.
No, you just have a mess.
You have a massive, chaotic database of ranges and angles. This is where we enter the processing crucible, because the actual flight is perhaps 10% of the work. The real engineering happens in the trajectory processing, which I like to refer to as the GPSI-CQ chain.
GPSI-CQ. Okay, break that acronym down for me.
Global Positioning System, Inertial Measurement, and Continuous Quality Control.
Let's visualize the raw data first, before we even get into that chain. Because it's kind of like the mist in a room analogy.
Oh, that's a good one.
Right. Imagine filling a room with a glowing, dense mist, where these microscopic droplets stick to every single surface. The walls, the couch, the ceiling fan. Then you remove the room entirely, leaving only the suspended mist.
So you just see the ghost of the room.
Exactly. You can clearly see the shape of the furniture based on where the mist settled. That is a raw, unclassified point cloud. But before we even think about turning that mist into CAD line work, we have to process the trajectory. We have to build the spine of the data set.
And the trajectory is the continuous microsecond by microsecond 3D path of the sensor during the flight. And it is computed by fusing 2 very different sensors together. First, you have the GNSS receiver tracking satellite constellations to determine absolute position in space.
Just normal GPS stuff.
Basically, yeah. But GNSS updates are relatively slow, maybe 10 or 20 times a second. Between those updates, the drone is moving and vibrating like crazy. So we rely on the IMU, the Inertial Measurement Unit. The IMU uses accelerometers and gyroscopes to measure the physical forces acting on the drone hundreds of times a second.
And we have to point out, not all IMUs are created equal. This is exactly where the cheap payloads fail spectacularly.
Oh, completely.
A standard microelectromechanical system, or a MEMS gyro, relies on this tiny microscopic vibrating structure. When the drone rotates, The Coriolis force alters that vibration, and the chip calculates the angular rate. But those MEMS chips are incredibly susceptible to temperature fluctuations and mechanical vibration drift.
They drift constantly.
Right. If you are flying a 30-minute corridor mission, the tiny microscopic errors in that MEMS chip compound over time. By the end of the flight, the IMU might honestly think straight down is actually 0.2 degrees to the left.
Exactly. This is why high-end surveying payloads use tactical-grade MEMS or even fiber optic gyroscopes. Those use the phase shift of light traveling through coils of optical fiber to measure rotation. They are vastly more stable.
But it costs a fortune.
They do. But regardless of the hardware, trajectory processing involves running these really complex Kalman filters forward and backward through the flight data. You are mathematically wrestling the slow GNSS positions and the fast drifting IMU measurements into a single cohesive flight path.
And if you mess that up,
if your trajectory is weak, like if you lost satellite lock because you banked too hard, or if you didn't do proper IMU calibration maneuvers before entering your flight lines, your entire data set is fundamentally warped. There's no fixing it later.
which leads instantly into strip alignment. Because once we have the trajectory, we project the laser data onto the Earth. We fly the site, basically like mowing a lawn down one line, turn around, fly the adjacent line with a 50% overlap.
The lawnmower pattern.
Yeah. And strip alignment is the lie detector test for everything we just talked about. We are comparing the data from strip A against the exact same physical space captured in strip B, flying in the opposite direction.
And if your calibration and trajectory are perfect, the points from strip A and strip B should interlock flawlessly. The pavement will look like a single crisp line in a cross-section.
What if they don't?
Well, if you have a 0.05 degree error in your pitch or roll estimation, the data from strip A might place the road surface at exactly 100 meters elevation, while strip B, viewing it from a different angle, places it at 100.1 meters.
So you get a 10-centimeter vertical bust. You get dual surfaces.
You get a ghost road, yes.
And a 10-centimeter bust on a hard surface is a total catastrophic failure for a surveyor. If a surveyor sees a dual surface on an asphalt road, the data is just rejected. You don't just smooth it out. You don't just average the two strips together to hide the error.
No, you can't just sweep it under the rug.
You have to go back into the raw trajectory, find out where the IMU lost its mind, and fix the physics. But, okay, let's assume the strips align perfectly. We have a pristine, crisp, beautifully aligned point cloud. To the computer, it is still just a dumb collection of X, Y, and Z coordinates. It doesn't know that a cluster of points is a high-voltage transmission tower or that a flat plane is a concrete pad.
Right, which brings us to the classification phase. We have to assign a mathematical class to every single point. Class 2 for ground, Class 6 for buildings, Class 14 for high-voltage wires.
And how does the software actually figure that out?
It uses geometric heuristics. It basically looks at a point and asks, are you the lowest point in a 5-meter radius? Yes. Does the angle between you and the next lowest point exceed 15 degrees? No. Okay, you are probably flat ground. It cascades these rules over and over to infer the structure of the world.
So what does this all mean for the human operator? Because the software algorithms are really aggressive now. They use machine learning architectures to segment these point clouds in a fraction of the time it used to take.
They are fast, but they aren't perfect.
All right, let's look at the bush that became ground scenario again. Say you have a drainage ditch. A thick, low-lying juniper bush is growing directly on the embankment. The automated routine runs, it sees the dense points on the bush, checks its local neighborhood, and mathematically decides, this gradient is smooth enough. This bush is the new ground surface. The ditch is suddenly modeled as being heavily constricted.
If we connect this to the bigger picture, it explains exactly why automation does not absolve liability. The human operator is the ultimate referee. You cannot just run a macro and deliver the output.
You have to actually look at it.
You have to pull horizontal cross-sections of the ditch, visually inspect the point geometry, manually highlight the points on that juniper bush, and reclassify them to Class 3, low vegetation. The software builds the rough draft, sure, but the human validates the physics. Bad classification is exactly where pretty data goes to lie.
Which perfectly frames the massive psychological trap of 3D modeling, the illusion of accuracy. We are biologically wired to trust high-resolution visual information.
We believe what we see.
Exactly. When a client puts on VR goggles and flies through a dense, colorized point cloud where they can literally read the license plates on the cars and see individual leaves on the trees, they implicitly assume the spatial coordinates of those objects are flawless. But But we have to ruthlessly separate precision from accuracy.
It is the single hardest concept to teach clients. Let's bypass the standard dartboard analogy for a second and look at what this means in the field.
Okay, let's do it.
Precision is internal consistency. It means your laser, your IMU, and your strip alignment are incredibly tight. The walls of a building are perfectly vertical. The curb is sharp. You can measure the width of a parking space and it reads exactly 2.5 meters. The internal geometry is flawless.
So the darts are grouped tightly together.
Exactly. But absolute accuracy is tying that internal geometry to the true global coordinate system of the Earth. You can have a flawlessly precise model of a building, but if your GNSS base station on the ground was set up over the wrong survey monument, or if you input the wrong antenna height by 1 meter, that entire perfectly precise building is shifted 1 meter deep into the Earth. It is a beautiful, hyper-precise model that is perfectly in the wrong place.
And the forces that degrade accuracy are just relentless. We talked about calibration, but we really must discuss bore sight and lever arm offsets.
Yes, the unseen gremlins of LiDAR.
Exactly. The bore sight is the exact angular alignment between the IMU's coordinate frame and the laser scanner's coordinate frame. They're physically bolted together, but nothing is perfect at a microscopic level. If the scanner is bolted 0.05 degrees off axis from the IMU, you have a bore sight error.
And that compounds quickly.
Let's do the math on that, because 0.05 degrees sounds like absolutely nothing.
It sounds negligible.
Right, but we are flying at an altitude.
Yeah.
If you're flying at 100 meters above ground level, the tangent of 0.05 degrees multiplied by 100 meters gives you an offset of nearly 9 centimeters on the ground.
Which is huge.
And when the drone flies back the other way, that error flips, creating an 18-centimeter horizontal divergence between the two flight lines.
Precisely. And then you have the lever arm. The lever arm is the physical distance between the face center of the GNSS antenna on top of the drone and the optical center of the laser scanner below it. If you measure that distance with a tape measure and you're off by 3 centimeters, that 3-centimeter error is permanently baked into the elevation of every single point the system generates.
It just shifts the whole world. And even if you dial in the bore sight and lever arm to the millimeter, you still have to fight the atmosphere and the environment. Most professional drone ops use RTK real-time kinematic positioning, relying on a local cellular VRS network to stream corrections to the drone via the internet.
Which is great until it isn't.
Exactly, because if you fly in a canyon or next to a heavy steel industrial facility, you encounter multipath.
And multipath destroys GNSS accuracy. RTK relies on calculating the exact carrier phase of the satellite signal. It's basically counting the literal number of wavelengths between the satellite in space and the antenna on the drone.
So it needs a straight line.
It absolutely needs line of sight. If the signal bounces off a glass skyscraper and then hits the drone antenna, the path traveled is longer than the direct line of sight. It adds extra wavelengths to the calculation.
So the math gets completely confused.
Right. The receiver fails to resolve the integer ambiguity. It drops from a highly accurate fixed solution to a degraded float solution, and suddenly your trajectory's positional accuracy balloons from 2 centimeters to half a meter.
Here's where it gets really interesting. How do you actually prove to an engineering firm that your data survives all of this? How do you prove the bore sight was tight, the lever arm was right, the RTK maintained a fixed solution, and the classification didn't turn a bush into a hill?
You use the polygraph test of the surveying world. You use checkpoints.
And we must strictly define the difference between ground control points and checkpoints, because operators frequently manipulate this to artificially inflate their accuracy reports.
Oh, all the time. It's a huge problem.
Right. A ground control point, or GCP, is a high-accuracy surveyed coordinate on the Earth that you actively feed into your trajectory or point cloud processing software. You use it to mathematically pull, stretch, and constrain the data to fit reality. GCPs help build the accuracy.
But a checkpoint is completely siloed. You survey a highly distinct feature on the hardscape, say, the corner of a specific painted arrow in a parking lot. You establish its true coordinate with a total station or a rover, but you absolutely do not give that coordinate to the processing software.
You hide it from the computer.
You lock it in a drawer. You process the entire multi-billion point data set blindly. Only at the very end, when the deliverable is finalized, do you overlay the point cloud onto the checkpoint.
It is the ultimate independent audit. You calculate the delta, the vertical and horizontal difference between where the point cloud plays the corner of that painted arrow and where the surveyor physically measured it.
And there are strict rules for this. The ASPRS, the American Society for Photogrammetry and Remote Sensing, they have stringent statistical standards for this. You need 20, 30, or 40 checkpoints distributed across a site. You calculate the root mean square error, the RMSE.
And if you cheat?
If you used a point to adjust the model, it is a GCP. It is disqualified from judging the final accuracy. A checkpoint is the honest, uncorrupted referee.
So we've just spent all this time outlining an incredibly fragile, highly technical, violently expensive workflow, calibrating gyros, resolving integer ambiguities, manually classifying brush, surveying independent checkpoints. It forces the ultimate business question. Is this massive effort actually worth it? Or are operators just pushing LiDAR because it's the most expensive line item they can sell?
Well, this is the dividing line between a technician and a consultant. A technician sells sensor time. A consultant sells reduced uncertainty. And frequently, the most ethical and effective way to reduce uncertainty is to leave the LiDAR in the case and just use photogrammetry.
Let's break down the detective versus the surveyor analogy, because I think it helps visualize this perfectly. Photogrammetry is the detective. A high-resolution camera takes thousands of overlapping 2D images. The software looks for unique visual clues, a specific crack in a rock, the sharp corner of a roof shingle.
Right, it's looking for patterns.
It finds that exact same pixel cluster in 15 different photos taken from 15 different angles in the sky. By calculating the parallax shift of those pixels, it triangulates a 3D coordinate. The detective reconstructs geometry purely from visual texture.
Whereas LiDAR is the surveyor. It doesn't look for visual clues at all. It blindly fires millions of distance measurements. And the detective is incredibly efficient when the visual clues are abundant and static.
Like on a bright, sunny day over a city.
Exactly. If you need to inspect the condition of concrete infrastructure or generate a high-resolution orthomosaic of a construction site, photogrammetry is visually superior. A LiDAR point cloud, even when colorized, looks granular and ghostly compared to a sub-millimeter photogrammetric mesh.
Wait, I need to look at this from the operator's business perspective for a second. Let's say a major commercial real estate firm is developing a massive 500-acre site. They have a massive budget. They call me and say, we want a full drone LiDAR scan of the property for our architectural planning and marketing package. We want the best.
They want all the bells and whistles.
Right. Why on earth would I talk them down to a photogrammetry mission that bills out at half the price? Aren't I just leaving money on the table to prove some academic point?
You aren't leaving money on the table. You are preserving your long-term reputation. Overselling technical complexity to a client who doesn't need it burns trust the exact moment they realize they can't use the data.
That's a fair point.
A marketing firm does not know how to open a 50-gigabyte LAS file. They want a visual mesh they can drop into Unreal Engine. If you explain the 5 layers of evidence, visual, location, elevation, structure, and decision evidence, you map the tool to the specific layer they need. They need visual and structural context. Photogrammetry delivers that better, faster, and cheaper. When you protect their budget, you become their trusted advisor.
Okay, so when does LiDAR actually win? When do you look at a scope of work and tell the client, yes, you absolutely must pay the premium for the laser?
When the environment actively weaponizes itself against photogrammetry. The first scenario we covered earlier, bare earth under vegetation. The detective cannot see the ground if it is visually obscured by leaves. No visual clues, no 3D geometry. The LiDAR surveyor threads the laser through the gaps.
Right.
The second scenario is complex industrial infrastructure. Imagine an oil refinery with massive multi-tiered pipe racks.
Oh, photogrammetry completely collapses in a pipe rack. The repetitive visual patterns of identical steel pipes just confuse the pixel matching algorithms. The shiny reflective metal blows out the camera sensor, creating visual noise.
They can't figure out what it's looking at.
And the incredibly complex, harsh shadows cast by the pipes essentially create black holes of data where the software can't find any tie points. The resulting photogrammetry mesh looks like melted wax.
Exactly. The detective is overwhelmed by the false clues and the shadows. The LiDAR sensor, though, ignores the shadows entirely because it provides its own light source. It pulses the steel, measures the return, and models the exact cylindrical geometry of the pipes.
That makes sense. What's the third scenario?
The third scenario is high-voltage power lines. Modeling a half-inch transmission wire suspended 100 feet in the air against a visually complex background of trees or sky is nearly impossible for photogrammetry. The wire is just too thin to provide reliable pixel matches.
But a high-density LiDAR system sweeping 400 lines per second will absolutely score direct hits on that conductor. You capture the catenary curve of the wire directly, which allows the utility engineers to calculate exactly how far that wire will sag under peak thermal load on a hot summer day and whether it will violate the clearance threshold of the oak tree growing underneath it.
It's all about precision on fine structures, and the final scenario is low-texture surfaces. Think of a freshly paved, massive asphalt parking lot, a snow-covered field, a massive concrete spillway. To a camera, these are just uniform seas of gray or white.
There's nothing to match.
There are no distinct visual features. The photogrammetry software will completely fail to generate dense geometry, but the LiDAR laser doesn't care about visual texture. It just needs a surface to bounce off of.
But choosing LiDAR brings an incredibly harsh operational reality. The mission demands the laser, but flying a surveyor-grade laser scanner completely changes the legal framework of your business. We have to talk about the payload tax. The aviation authorities do not care about the resolution of your data. They care about the kinetic energy of your aircraft falling out of the sky.
And heavy. Accurate glass is heavy. A professional LiDAR scanner, the tactical-grade IMU, the ruggedized housing, the stabilized gimbal, and the massive lithium polymer batteries required to keep an 8-rotor drone in the air for 30 minutes. I mean, it adds up exponentially.
In the United States, standard commercial drone operations fall under 14 CFR Part 107. But Part 107 has a hard weight limit. The entire aircraft, payload included, must weigh less than 55 pounds at takeoff. A high-end LiDAR rig mounted to a heavy-lift platform like an Alta X or a DJI M350 can easily push right up against that limit or just shatter it entirely.
And once you cross that line,
The second your takeoff weight hits 55.01 pounds, you are suddenly operating an entirely different class of aircraft in the eyes of the FAA. You need a Section 44807 exemption, you might need a pilot with an actual manned aviation certificate, and your operational parameters are heavily restricted.
the regulatory landscape dictates the operational economics. We have to look impartially at how airspace is managed globally. Let's examine the Canadian airspace model, for example, which underwent a massive transformation with the 2025 RPAS expansion, specifically the SOR 2025-70 amendments.
Right, that was a huge shift.
Transport Canada recognized that to unlock the economic value of drone LiDAR for massive infrastructure projects like pipeline inspections or forestry management, they needed a scalable pathway for beyond visual line of sight, or BVLOS, flights.
Because before this, BVLOS in Canada required a Special Flight Operations Certificate, an SFOC, which was just a slow, agonizing process.
Correct. But the new framework established a structured path. It introduced the RPAS Operator Certificate, the RPOC. To get an RPOC, a company must prove they have robust safety management systems, standardized maintenance protocols, and rigorous pilot training programs. It's much like a traditional manned airline.
You have to act like a real airline.
Exactly. Additionally, the pilot must hold a Level 1 complex certification. If you meet these organizational and individual hurdles, and you are flying a certified drone in uncontrolled airspace below 400 feet and maintaining a strict standoff distance from populated areas, you can fly BVLOS. It is highly structured, deeply audited, and heavily regulated.
Compare that to the U.S. framework as of our current timeline in April 2026. Part 107 remains the active, everyday law of the land. If you want to fly a 10-mile power line corridor without moving your visual observers every half mile, you need a specific Part 107 BVLOS waiver.
Which is not easy to get.
No. It requires proving to the FAA that your detect and avoid technology and operational mitigations provide an equivalent level of safety to a human pilot looking at the sky.
The FAA did release the Notice of Proposed Rulemaking for Part 108, which aims to create a standardized performance-based rule for routine BVLOS operations. It focuses on the specific operations risk assessment, the SOAR methodology, defining risk based on the kinetic energy of the drone and the population density below it. But proposed rules are simply proposals. Professionals operate under the active law.
This raises the ultimate trap of technology. I've seen operators buy incredibly advanced LiDAR drones equipped with 360-degree millimeter wave radar, terrain following sensors, and triple redundant flight controllers. They look at this flying supercomputer and think, the technology is flawless. I don't need to follow the drone down the pipeline. The sensors will prevent a crash. Can they just launch the drone, sit in their air-conditioned truck, and let the software run a 5-mile corridor mission?
This raises an important question regarding the philosophy of aviation automation, and the absolute answer is no. BVLOS is not a technological feature of your drone. BVLO is a regulatory authorization.
That is such a crucial distinction.
Replacing human visual control with a sensor suite is only legally valid if that sensor suite has been rigorously validated, certified, and approved by the Aviation Authority as a defensible system of risk controls. Your 360-degree radar might detect a power line, but can it detect a non-transmitting paraglider descending through your flight path at 60 miles an hour?
Probably not.
Technology does not erase your legal requirement to see and avoid other aircraft. The LiDAR sensor maps the Earth. It does not shield you from federal aviation law.
It is a sobering reality check. You can execute a flawless trajectory, align your strips perfectly, classify the ground with pinpoint precision, and prove it all against independent checkpoints. You can hold the most accurate data on Earth on your hard drive. But if you collected it outside of your regulatory bounds, your business is a massive liability. You aren't just a data scientist. You are an aviation operator.
Operating a LiDAR system elevates a business into a tier where advanced photogrammetry, rigorous land surveying principles, and strict aviation compliance all intersect. You cannot simply master the software. You have to respect the physics, validate the mathematics, and operate within the law.
So let's tie this entire deep dive together. We started with the illusion of magic, the idea that a drone just captures a perfect 3D model. We've torn that down. LiDAR is an active remote sensing method that fires microscopic laser pulses to capture a chaotic field of evidence.
Just raw evidence.
And that evidence is useless without a flawless trajectory generated by highly stable IMUs and tightly coupled GNSS. Even then, the data must survive the crucible of strip alignment, the meticulous sorting of classification, and the brutal reality check of independent surveyed checkpoints. And you only engage this incredibly heavy, expensive, highly regulated workflow when the mission demands structural truth over visual context.
Which leaves us with a final, rather provocative thought regarding the future of this industry. Throughout this entire workflow, we have emphasized the absolute necessity of the human operator acting as the honest referee. The human validates the IMU alignment. The human ensures the algorithm didn't classify a thicket of brush as a drainage ditch. The human holds the checkpoints independent to prove the accuracy.
The human is the firewall against bad data.
Precisely. But right now, automated AI processing is becoming exponentially faster and vastly more aggressive. Deep learning algorithms are being trained to ingest raw, unaligned LiDAR mist, automatically correct the boresight errors, auto-classify the terrain, and export a finished 3D model in a fraction of the time it takes a human to even open the software.
Which sounds great for business, but
as these algorithms get better at hiding the raw, chaotic reality of the data underneath a perfectly smooth digital twin, what happens to our critical oversight? If the AI generates a model that looks visually flawless, will operators slowly stop running the independent polygraph tests? Will we surrender our skepticism to the convenience of the algorithm? Because if we do, we risk building incredibly beautiful, highly precise, entirely automated 3D worlds that are absolutely confidently wrong.
that is a terrifying, brilliant thought to end on. Because when the AI hallucinates a ground surface and the concrete is poured backward, the software algorithm will never be the one standing in front of a judge answering for a multi-million-dollar engineering failure. You will. Thank you for joining us on this deep dive into the granular mathematical reality of LiDAR. The next time you see a 3D digital twin of a city block, a power line corridor, or a forest canopy, I hope you don't just see a magical recreation. I hope you see the laser pulses, the trajectory math, and the physics of the capture. I hope you look at the spatial data you use every day with a newly skeptical, highly informed eye. Until next time, keep questioning the magic.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.